filibuster here while you
Yeah,
get in there?
it should take a second.
Right.
Is that better? Okay. There you go. Thank you. So I'm Ryan Goen, and I'm a PhD student in Professor Mingwu's lab at UC Berkeley. And as you might guess from the title, I'm going to talk more about a single device and an optical link, moving away from the whole system perspective. And specifically, we're looking at the photoreceivers in the link and how to improve the performance of those so we don't have to put in so much optical power. So we just had a lot of wonderful introduction on why the energy per bit problem for optical interconnects is still an issue. And one thing that we specifically focused on was the photoreceiver. Specifically, we can scale a photodiode capacitance to enhance the sensitivity and reduce the total number of photons we need to send in for a single bit of information. But one of the issues that we start to come upon when we start shrinking these photodiodes down to sort of the femtofarad scale of capacitance is that we actually have to start thinking about the wires connecting these photodiodes to the receiver circuitry. So for example, just 5 microns of wire connecting the photodiode to the receiver is going to have 1 femtofarad of capacitance, which if we have a 1 femtofarad photodiode, we've just totally eliminated all the work we've done to shrink it down. And so the idea behind this is integrating these two together, much like a phototransistor or avalanche detector, some sort of device with gain. And so a lot of people have done this recently, especially in Germanium. There's a lot of different architectures you could choose from: bipolar, avalanche detectors, junction field effect transistors, poly-germanium gate transistors, and what I'm going to talk about here today is a single crystal germanium gate phototransistor or PhotoMOSFET. And so the basic design of what we did was we put a silicon body NMOS on the silicon photonics layer. So our silicon body and our silicon photonics waveguides, grating couplers, everything else you might want in the photonics is in the same silicon layer. And then we simply build a germanium gate on top of that. And this germanium gate, when the light evanescently couples into the germanium gate, essentially it's an open circuit photodiode. So the photocurrent has nowhere to go. And what this does is creates an open circuit voltage in this germanium gate. And so the action that happens is that when the germanium absorbs light, we get an extra gate voltage on our MOSFET, and this translates into an enhanced drain current in the MOSFET. Specifically, how we get the germanium on there is we utilize the rapid melt growth technique. So this technique allows you to get crystalline germanium on oxide. And the way that happens is you deposit your germanium on oxide, either with CVD, evaporation, sputtering, and you leave a little section of the oxide open down to the silicon, which acts as a crystal seed. After you pattern the germanium into your desired shape, you enclose it with more oxide, and you actually ramp it up to melting temperature. We chose about 1,000 degrees C for just a second or two, and when you cool it back down, this silicon seed actually propagates, and you get single crystal germanium all along your shape. We incorporate this into our basic process flow, so we make our silicon photonic structures, thermalize our oxide, and pattern our germanium gate. We then do a self-aligned implant to give our source and drain and implant the germanium gate as well, N-type. And then we do our rapid melt growth simultaneously with the dopant activation. Finally, we just open up some contacts and put metal down, and you can see a optical microscope of a final device. So we have our grating couplers to couple into our devices, the waveguides that taper down to a single mode, and then in the inset you can actually see this is our silicon seed, our germanium line, and the body of the MOSFET. So as expected, we probe these just with a single fiber to probe into the grating coupler. But basically, once the light is in the waveguide, that's sort of what we're accounting for. And we use 1550 nanometer light. And as you might expect, if you look at the drain current versus gate voltage curve, when you put in light, you get more current out. But the more interesting thing about this is that if you actually look at these curves, you see that as you shine light on there, the curve shape doesn't change. What happens is it just shifts. And so this is supporting the idea that we're not just generating photocurrent in the device. We're specifically generating a gate voltage on the MOSFET, and that's generating our photocurrent with our gain. And what this means is that we can actually choose the region of operation for our MOSFET to operate in to give us our gain. Because we're just getting an extra gate voltage, we can operate in a linear saturation, subthreshold, whichever we choose. And specifically, we're just going to get an extra gate voltage on the device. What that means is that if we extract the responsivity of our device, the responsivity is going to be a function of our electrical bias as well as the optical bias. So the other really interesting thing about this device is that it's very, very sensitive at low optical powers. So when we put in half a microwatt of optical power, just by adjusting the gate and drain biases, we were able to get upwards of 18 amps per watt. So that sort of exemplifies the high amount of gain we're able to produce from this relatively small device. But the interesting thing is that if we move to higher optical powers, such as half a milliwatt, the responsivity seems to go down a little bit. In this case, about 150 milliamps per watt. And the reason this might seem a little contradictory is we have to actually go back and look at what's happening in this device. So if we consider that the germanium gate is a photodiode, it's an open circuit photodiode specifically, then we can actually calculate the voltage induced in it just by the optical input power. And from the diode equation, what this says is that the photovoltage is going to go as the log of the incident power. And it's going to have this KT over Q factor out front. So what that means is that with this specific gated PhotoMOSFET device, for every decade, or for every factor of 10 increase in optical power, we're going to get a 60 millivolt increase in gate voltage. And that's sort of fundamental to the physics of the device. However, we also have these constant terms on the end, and these are the things that we can actually play with. And these are dictated simply by the crystal quality and, more importantly, the geometry of the device. So by shrinking the geometry of the device, we can actually make this more sensitive by shifting this curve to the left there. And that has some interesting implications for the scaling of this. And then finally, we looked at, so this is a 1 micron channel device. It's 8 microns long. And you can sort of calculate, you can estimate the capacitances involved in this device. And you get about, this one's relatively large, it's about 25, 30 femtofarads. And if you put these into the basic MOSFET equations, that should have a bandwidth of about 2.9 gigahertz. And what we were able to measure optically with the network analyzer was about 2.5 gigahertz. So this seems to imply that this device is at least transit limited in a more traditional MOSFET sense. Again, that's also emphasizing that you can get a speed improvement from these devices simply by shrinking the gate length. So that's good news. So what we did next was we did a few simulations of these, scaling down the gate length to see what will happen. And we sort of normalized these against the measured data that we collected. And the nice thing is that, so going just from a 1 micron gate length to a 250 nanometer gate length, the overall bandwidth of the device should increase to upwards of 28 gigahertz. So now we're starting to move more towards the more mainstream reported speeds of 25, 40 gigabits per second. And the other interesting thing is that simultaneously with the increase in speed, we also get an increase in responsivity. And that's because I talked about that shrinking of the diode area. So we're going to go from 18 amps per watt up to 150 amps per watt. So this is just with the standard constant field scaling. So shrinking the gate oxide channel length, etc. So the main point that I just wanted to get across was that this is a rather interesting device utilizing specifically this unique germanium on silicon device. It's a 1 micron channel length, so it's very old, very long channel technology, but we're able to get relatively high responsivity and relatively high speed. And more importantly, what we were able to show with some theory and simulations is that this is scalable, and that even just scaling down by a factor of 4 to a 250 nanometer gate, the bandwidth and responsivity should be vastly improved. So with that, I want to thank the Mingwu group, Jody Liu, who is an undergrad in our lab and did a lot of measurements, and funding from E3S Intel and the NSF. Thanks.
All right, time for comments and questions.
Yeah.
So we heard that one of the big cost factors had to do with the laser and the cost of the laser and the cost per photon. So what's normally done in silicon photonics is a simple photodiode. How much more sensitivity, how much better signal to noise do you think you can achieve compared to a conventional system?
That's a good question. This is a research device, but one of the primary benefits here is that with the tight sort of photodiode to receiver integration, the overall sensitivity should be dramatically improved, probably on the order of maybe orders of magnitude improvement is sort of the idea. So moving from picojoule per bit receiver energy to maybe femtojoule per bit receiver energy or something along those lines. That's sort of the main idea of the tight integration there.
When you scale the gate length, do you have trouble coupling in the laser light?
So one of the things that I didn't specifically mention, but is actually rather nice about this type of device, is the natural geometry of a gate on a MOSFET. It's a long line, and that sort of naturally lends itself to a typical waveguide geometry. So even with 250 nanometers, if you make your gate sort of long enough along the waveguide, you can absorb most of the light. So it doesn't really become an issue until you start to get below 250, 200 nanometers. And for this specific wavelength, then you start have to coming up with some tricks to get more absorption.
Is your component susceptible to dark current, and if so, how would you mitigate that with your?
Right. So sort of buried, there is dark current, and it's buried in the photovoltage of the device. So I mentioned that there's this photovoltage as a function of the incident power, and then there's these constant terms on the end. And one of those constant terms is dependent on sort of the diode leakage current of that sort of gate quasi-diode structure. So by reducing that dark current, that dark leakage current within the diode, which is very, very closely related to the quality of the crystal, you can get a higher photovoltage for a lower incident optical power. So I did the measurements on this. So this is a 1 micron by 8 micron sort of germanium diode, and the effective dark leakage current was about 100 nanoamps for this. So it's kind of middle of the pack from what I've seen.
How would that scale as you reduce your size to go to high speed?
Right. So in theory, it should. Right. So the overall the current density should remain roughly the same. So the overall dark current will shrink, and so that's sort of taken into account in that scaling idea, which is that you're shrinking the area, so you're shrinking that total dark leakage current in your diode, and that's going to increase your sensitivity.
Okay. Thank you very much.